My name is François-Xavier Becot, and I will present you I will introduce this webinar from the experimental characterization to very simple acoustic simulation with which you can design some material treatments. At first, I will present Matelys as generally speaking. Matelys is in France first. It's located in Lyon, which is a very nice town. It's capital of the French gastronomy. And it's also a beautiful town with a medieval part, and you're most welcome to stop by and say hello to me if you have the chance to come to Lyon to visit us. First, I would like to introduce a little bit what Matelys is doing about the activities. So Matelys is an independent research laboratory which expertise covers materials, of course, acoustics, mechanics, but also thermodynamics and flows, which is probably not so common to most of you. So in activities we are addressing the building activities, of course, transportation, which are the two main activities, but we are also addressing the other industries, and also piping activities for monitoring the sound and vibration, which is transmitted through the pipes or ducts. About the services that we provide some characterization activities, so both characterization of the material properties and also characterization of the sound sources as a running source that you have here. This is a delivery trolley. We, of course, based on this knowledge, we can provide some recommendation for material usage. The core of our activities is also R&D activities, developing models for handling some new or innovative materials, but also materials in other or in elaborated or complex configuration. We, of course, provide some training activities, educational program in-house, on-site, and we developed a special tools, what we call smart tools, based on web application. Of course, I will not come into details about all these activities, but you're most welcome to contact me later on if you want to know more about this. We also developed some products for acoustic simulation, of course, and I will mention today a little bit more about Alphacell. We also provide a tool for handling material database. We provide some tools for measurement and characterization, and I will talk about later on Rockcell, which handles the characterization of porous materials and screens and liners. We also provide some tools for characterizing and simulating the flow or the sound propagation in pipes or ducts. And we finally provide some turnkey test rigs for characterizing the acoustical and mechanical or elastical properties of the porous materials. Okay, let me first start to introduce a little bit more what our activities are embedded into a typical engineering workflow. So material design would go like this. You first start with the material design, talking with the chemists, and you have two ways to come into the sound package design, either experimental way or virtual way. We provide some tools for both ways, but at the end you would like to simulate and to predict the response of your sound package to some given excitation. That's where Alphacell comes in. But if you would like to have to validate further the results of your simulation, then you should come to Actran, a more elaborate elaborated computational tool like Finite Element and like Actran is providing. So that's how how I could draw the typical engineering workflow. So about the characterization, the provision of the material properties, I would like to draw in 3 slides how we could access to the material properties. So we first measure directly the airflow resistivity. We also measure the porosity, and we, based on impedance tube measurements, we do an analytical inversion of some predicting model. We use the Johnson, Shampoo, Alarm, Lafarge model, which is a 6 parameters model. And I would like to emphasize that this is not a minimization, so this is a more robust determination. So in a little bit more detail, so you measure the airflow resistivity, so that's practical because you have a standard for this. We measure the porosity, which is direct measurement of the porosity. And at last, we measure in impedance tube 2 quantities which are typical for material properties, which are complex and frequency dependent. This is the mass density and the compressibility. So you have a number of methods based on impedance tube measurements to retrieve these 2 quantities. The most important is that these 2 quantities are connected to visco-inertial dissipation and also to thermal dissipation. And these are separate effects. And based on the description provided by Johnson, Shampoo, Alain, Lafarge model, you could separate these 2 effects and connect them to some predicting parameters. And if you invert them, so you finally obtain a system of equations, of 4 equations with 4 unknowns, and you can invert this well-posed system of equations to retrieve the tortuosity, the viscous and thermal characteristic length, and the static thermal permeability. So at last you have an analytical inversion of some model, and also you have, well, this is supported by 2 direct measurements of 2 quantities, the static airflow resistivity and the porosity. Okay, shall we go for a short demo of Roxer, just to show how is it done. So I'm not sure you see my application, so just give me a second so that I share the application. Okay, so this is the Roxer characterization assistant. So you load the measurement file, okay? So this is the envelope of the measurement. So in terms of mean plus or minus the standard deviation for each frequency point. And then for a given sample, you provide first the porosity, okay? You provide the airflow resistivity, and you can characterize the viscous effect, the thermal effect. So you have some parameters. You have, therefore, the analytical expression of the tortuosity as a function of the frequency. The same for the viscous characteristic length. For the thermal effect, you have the thermal characteristic length and the static thermal permeability, which is low frequency parameters, so you have to fit a little bit more in the low frequency range. Once you are satisfied with that, you can compare the measurement with the prediction. You see that it's fairly correct. So this validates the set of parameters that you have characterized. You can do that for any of these samples, of these measurement samples, and at last you would have a good correspondence with your dispersion on the measurement. So that's how you could retrieve the material properties. What is more interesting here is that I can export directly with this tool. Sorry, I will put in English. would be more practical for you to read. I can provide an Actran material card, which I'll just show you in a minute. I will put that on the desktop here. So this was material desktop, okay. So give me a minute now. Here it is. You should see that this is a material card with the given material properties in terms of fluid density, sound speed, porosity, tortuosity, etc. This material card may be used directly under Actran to create a new material in your model. Okay, if I now come back to the presentation. Now, if I would like to simulate, and if I would like to have quick and very simple simulation, we could use TMM approach. What is the TMM approach? Well, if I would like to compare with finite element, I would start like this. I will start with the real-life picture. Here you have the sand, you have some stones, you have the seashore here, and the sea a little bit further away, and the sky on the background. If I would like to model this with a finite element, I would model any of the layers, including the very detailed object of the picture, including the stone. Okay, so I will have a very fine description of the picture. Now, if I would like to model this using transfer matrix method, TMM, then it would go like this. I would have only 3 layers with equivalent parameters. This layer would be flat, infinitely long laterally speaking, with equivalent properties, which means that for the bottom layer, which includes stones here, I would have some parameters which account for the presence of the stones, but which are somewhere in between, so to say, between the sand and the stones. So this is an homogeneous layer, but it could include the presence of the stone if possible. So these are the main assumptions of the TMM compared to finite element model. What I can model with this approach? Well, basically any kind of model. I can model some cellular materials, including open cell forms or closed cell forms, including viscoelastic forms. I can model, of course, fibrous materials. Might there be single porosity or double porosity? I can model, of course, shoddy, which we find quite commonly in the automotive industry. We can model, of course, orthotropic material, taking into account the fact that the properties in plane are different from the out-of-thickness properties. We can model granular properties, granular materials, sorry. We can also model perforated plates, fabrics, and non-woven layers. We can also model viscoelastic materials, and by viscoelastic, I mean frequency-dependent material parameters. So what is the point, in fact, of having all these categories of material? Well, because you have 2 different configurations, what you can encounter. The first one is a sound absorption, where the source and the receiver are located in the same room. And you have another picture where we talk more about sound insulation, where the source and the receiver are separated by some wall and some separating layers. I would like, with these 2 very simple pictures, to highlight that in the 2 cases, the materials are very different, and a material which is good for sound absorption is not obviously good for sound insulation, and vice versa. A material which dampens the sound which is transmitted into the other room is probably not the best for making a very good sound absorption in a given room. Okay? So, in fact, you would have materials and strategies which are different depending on which configuration you are placing yourself. Okay, so I will end up my talk with a demo of Alphacell, just to give you an idea of how simple is it with this kind of application. So give me a second, I will share my screen. Here it is. So this is Alphacell interface. I've created a project here, a study, which Diego Copiello will talk about later on. So I just load this case. This is made of a aluminum layer, which is 1 millimeter thick. There is a felt, typically used in automotive, with a given mass density. You have here the material parameters which are used to describe this felt. And you have a screen here, which is modeled as a perforated plate. I would like to emphasize that the deformation of the elastic plate, of the perforated plate, is taken into account using a very original numerical scheme. We have a publication about this scheme, so if you are interested in knowing a little bit more about that, I can share with you the publication. So here is my model. You have here, and just zoom in a little bit, I have my aluminum foil, my foam, and the screen here. And to build my model, I can just drag and drop the material parameters, and once I am satisfied, I choose the backing condition here, and once I am satisfied, I can directly click to compute in this case, the sound transmission loss in decibels for this configuration. Okay, this will take a few seconds more. I will just show here that you have some additional information about the layer. You can provide here, make visible the information about the critical frequency, the quarter wavelength, and this information would be interesting in the fact that if you would like to interpret the results, for instance here, what is this dip corresponding to? Well, you could look that it's located around 1500 hertz, which is closely located to the quarter wavelength resonance frequency within the layer. So if you take another material, for instance this one here, I will superimpose the curves. I will run the simulation again. If I look at the quarter wavelength resonance, it's located around 500 hertz in this case. So I should expect here a dip in the sound transmission curve around, in this frequency region, around 500 hertz, which is the case here, okay? So this is, and I will stop here the simulation. This is just to show you that it's very simple to understand the material behavior. If you would like, again, to have more details and validate further your results, then you should come to a more elaborated code, like finite element code, like Actran is doing. So I will give out the end to Diego now, which will present further the link between Alphacell and the finite element code Actran. Thank you.
Okay, so first of all, thank you very much, François-Xavier, and let's see now how we can integrate all this information within Actran. To this aim, let me recall what are the design objectives. As François-Xavier already described it, what is the difference between sound absorption and insulation. The porous materials are extensively used to reduce, for example, the sound transmission between two environments or to increase the sound absorption within a specific closed volume. Therefore, we find porous materials basically everywhere, such as windows, frames, or doors, and you can find porous materials also in aircraft fuselage and car compartments. For example, and this will be the demo of today's webinar, we see here a car structure. The dashboard is composed by a multi-layered material, and it is also used to reduce the sound transmission from the engine bay to the interior compartment. Moreover, porous materials are also applied to the floor, for example, to increase the sound absorption inside the car and improve the comfort of the passengers. In the case that we want to design the car dashboard, which is constituted by a multi-layer structure, we need the following modeling capabilities. First of all, porous material models and parameters to characterize them. For this, we will use the input data provided by our partner. A noise source, which is in this case a diffuse sound field applied to the engine side of the dashboard. We'll see what are the possibilities available in Actran to the same. And then we will need both the acoustic domain and the structural part modeling capabilities to actually include the car behavior which is affecting the system response. Finally, it is worth to note that to actually design the dashboard, typically the noise reduction index is used, which is linked to the ratio between the mean pressure applied to the exterior of the dashboard and the mean pressure computed inside the car volume. In other words, the higher the noise reduction index, the better the acoustic performance of the dashboard. So first of all, to model a car dashboard, we need an FEM code to actually model all the peculiarities of the system. Indeed, as François Xavier has already mentioned, if you want to model a physics that is closer to the real world, you need to take into account more details to obtain responses closer to the real behavior of the system. And to this aim, the FEM method is a perfect tool. Its computational process is quite standard. So first the model is set up including the generation of the acoustic mesh, then the computation is performed, and finally the post-processing is carried out to obtain the desired design metrics. Now Actran is an FEM code, so it follows this process, but it is slightly different, as indeed it features the adaptive meshing technology, which is specific to Actran, and changes this process as the acoustic mesh now is automatically made and optimized by the solver itself. This allows first to reduce the user effort, and then it allows to generate a set of acoustic meshes optimized for different frequency bands, allowing a drastic improvement of the computational performance. For those of you who are not familiar with the Actran software suite, well, Actran is divided in different modules targeting different applications. The basic module is Actran Acoustics for computing acoustic propagation, and then we have two modules dedicated for vibroacoustics. The first one is Actran Vibroacoustic for fully coupled vibroacoustic problems, and Actran for trim body, which is dedicated for computing the vibroacoustic response of large trimmed bodies such as car cabins or aircraft fuselages. Then we have two aeroacoustic modules. One is Actran Aeroacoustics for computing the noise generated from turbulent flows, and Actran SNGR, which is used for computing for making aeroacoustic computation, but starting from steady run solution. So it's a cheaper solution compared to the standard aeroacoustics. Then we have Actran TM dedicated to turbomachinery noise, and Actran DGM for computing the noise in large domains or at very high frequencies. Actran features also a set of possible parallelisms and a dedicated GUI that we will see during this demo. Today we will focus mainly on Actran vibroacoustics, although for achieving superior computational performances for the problems involved, Actran for trim body can be also considered. Now, as we have just discussed, Actran is a finite element code, and finite elements are used for modeling fluid domains and structural elements, such as viscoelastic solid, thin shells, or one-link connection like rigid bodies. concerning the structural elements, it is worth to note that Actran VI, the graphical user interface, is fully compatible with Nastran. This means that an Actran input file can be imported into Actran VI, and all the Nastran cards will be converted into Actran's components, so it is possible to enrich the model with any Actran feature. Moreover, with the aim of having a representation closer to real life, we can also include Nastran model responses, of course, but also super elements are supported as well. Concerning the solution approaches, there are different options. The first one is the direct frequency approach, where a model is completely solved in physical coordinates. The second option is the model frequency approach, where the solution is obtained in model coordinates. And finally, we have the hybrid approach, which leverage both the advantages of the direct and model representation. So for example, concerning a porous material, which involves complex dissipation mechanisms, it shall be represented in direct coordinates, whereas a structure is better represented in model coordinates, as this reduces the number of degrees of freedom of the system and therefore allows to improve the system performance. So why do we need to investigate porous materials? Porous materials have multiple energy dissipation mechanisms, some specific to their biphasic nature too. These dissipation mechanisms make porous materials an excellent choice for limiting sound and vibration. And to this aim, porous materials are modeled by means of the biot formulation, since it's numerically attractive for computational reasons, it's easy to couple with solids and fluids, and also the anisotropic formulation is available. Now, this formulation needs as input the skeleton properties, so the Young modulus, density and the Poisson ratio, the fluid properties, so the fluid density, the speed of sound, and so on, and the skeleton to fluid interaction properties, such as the tortuosity, resistivity, and porosity. Moreover, at a microscopic level, porous materials are a complex network of pores and channels. Therefore, local viscothermal effects have a strong influence on the microscopic behavior. These microscopic viscothermal effects are modeled with dedicated micro-models available in Actran, which are the same models implemented by Matelys, and thus there is perfect support. To model a porous material, then we need several parameters that can easily be detected by experiments, but also some simplified models or semi-empirical models are available in Actran on the basis of the assumption that can be made on specific cases. Then, to study the dashboard that we were discussing earlier, what kind of excitation do we apply? Specifically, what kind of excitation do we apply when we consider multi-layer parts, such as the dashboard, as I said, or window system, or an aircraft fuselage? Well, in the specific case of the dashboard, we will apply a diffuse sound field, which is fully characterized by the statistical properties of it, which are known analytically. In other words, this is a random excitation, and it is described by a set of samples having a certain spatial correlation. Other different random excitation are available in Actran, such as the turbulent boundary layer or the rain on the roof model. If on the one hand these are excitation different from a physical perspective, they are very similar from an implementation point of view. In any case, the results provided will be both deterministic for each stochastic process, and dispersion indication will also be available. Finally, to have fast response of the system, the computation must be very efficient, and to this aim, the mesh adaptivity is a fundamental technology which allows improving dramatically the computational performance. The mesh adaptivity is available in Actran, and it is extremely efficient. How does it work? Well, the mesh is generated by the solver, so it is automatically generated, and it is optimized for given frequency bands. Therefore, for low frequency bands, we will have coarse meshes, whereas for higher frequencies, we will have a mesh that is finer to correctly capture the shorter wavelengths. We can see here a benchmark of an interior of a car problem, similar to what we will see later. where we have reached a speed up of the computation of a factor of about 4 times compared to a standard acoustic computation. Okay, we can see now the demo. As I mentioned earlier, the demo is related to a car dashboard. I have built this demo on the base of Actran 16 release that is released, actually is currently released, so it has been released today and it will be announced officially tomorrow. So it is slightly different for the users that are listening to us compared to what they are used to see. Nevertheless, this is the car cavity, where we have, first of all, the 3D domain that is in here, and it will be linked to the to the acoustic domain. Then we have all the structural parts. So we have, first of all, the dashboard, which is here, which is discretized by a thin shell, so 2D elements. Then we have the porous material, which is on top of the dashboard, which is discretized by 3D elements. And then we have the screen layer, which is on the other side. It is made by a perforated material. This is all concerning the topology and the domain and the mesh. So we can go through the materials that are here. So we have, first of all, 2 isotropic materials, the aluminum of the dashboard. So we have, if we open and check the properties, we will have the Young modulus, the Poisson ratio, and the solid density. Then we have also the screen layer that is an isotropic, described by an isotropic material and a perforation material. So in the perforation material, we will find here all the description of the perforation, so the radius of the perforation, the thickness of the plates, the perforation distance, and the geometry of the perforation. Then we have also some porous materials that have been imported directly from the exported files provided by Alphacell, for example. So to import them, I will show how to do it. We right-click on the material, and we select Import Materials. Now we are exactly in one folder that I have created with all the material cards that have been provided by our partner. So for example, I will open this material, which will be exactly here, and this is my porous material with all the parameters that have been characterized from an experimental point of view. I will look at the result through the PLT viewer, and here we see the noise reduction index for this case for the 2 different foams. So what we see is that the light foam is performing better at low frequency compared to the heavy foam, from 0 to something like from 30 Hz up to something like 70 Hz. Then the other heavy foam is instead performing better than the light foam between 70 Hz up to 130 Hz. Then we have a range of frequencies where basically we cannot directly say which one is better, and it is from 130 Hz up to 400 Hz. And then for higher frequencies, we have the heavy foam that is again performing better than the light foam. So let me conclude this webinar. And porous materials are widely used to ensure comfort and superior product quality. Porous materials are typically modeled with a bias formulation, which requires several parameters, but these parameters can be detected easily and very quickly from experiments. To design products involving porous materials, one could first use a TMM method to rapidly assess several designs up to very high frequencies. Then results can be validated on Actran, which allow to perform simulation of models closer to reality, as you can apply realistic boundary conditions, such as the full car structure influence, or consider the realistic environment, such as a full car cavity. This is all from my side. Thank you very much.